And we're rolling. Any questions? Yeah, please.
Yeah, so for the lab, so this is for the most recent lab that we've had, did you say that, that the force for the meter stick was a negative force?
Yeah, because the force of the meter stick is the weight of the meter stick, which is acting downwards.
Okay.
And I set up the convention of up is positive, down is negative.
All right, I was making sure.
Okay. Any other questions?
Okay, for the test, are you able to answer a question on the test that we just had?
Yeah, I think everyone in here has taken it.
Okay. Yeah, for 4E, I know, so you were just telling me about this question, but how would you find the magnitude of the weight of the beam in,
Okay, it still goes back to there's two forces acting up and two forces acting down.
yeah, and they cancel out, right?
Right, they're gonna cancel out. So you know the total force acting up because I gave you that gave you those numbers and you add them together. So that has to equal the total force acting down. The total force acting down, there's two forces there. There's one that comes from the weight of the person, which you know, and the rest of it has to come from the weight of the beam.
Okay.
So weight of the person plus weight of the beam must equal the two tensions acting upwards.
Okay.
Yes, Ben.
Do we have 6 class left?
So 1, 2, 3.
Yeah, this week and next week?
5 left because we don't have class Friday of next week.
Including this one?
Yes, including this one.
So soon, okay.
And one is lab day, like this Wednesday?
This Wednesday is lab day, but we're gonna not do a formal lab.
Like, we will do a lab or?
No, we'll, I'll talk later about what we're doing on Wednesday.
Wait, so sorry, so this is gonna be our last lab, that's,
Yes, that'll be the last lab you're handing in.
okay.
If I see little drops of tear stains on it, I will know it's,
Because we're so sad. that-
yeah, because it's the last one. Okay. Any other questions? All right, let's hit those last two rotational motion bits. When we talked about an object rolling, so let's assume there's static friction, so no slipping. In other words, we're gonna get a perfect roll here. In reality, if you have an object rolling, you know, we can do nice physics problems where I have a ball sitting on top of some flat surface. See how well this one works. But if we zoom in, there's gonna be a small little indentation in whatever the surface is. And with that small, since there's more than one point of contact here, there will be some slipping involved, and so that's why you do end up with a eventual loss. If I roll a ball on the carpet, it will eventually stop. If I do it in the hallway, it will go farther because there will be less in, the floor is not gonna give as much, but eventually it would stop if I rolled a ball in the hallway, presumably slowly enough so that it's not gonna hit a wall. But we're gonna assume a nice ideal perfect roll here. I think we left off with the question of what is the actual pivot point? And I think Ian had said.
Yeah, it's at the point that it's touching.
Yeah. So let's think about we're in that situation where not everything on the ball is traveling at the same speed. So my kinetic energy, 1/2 I omega squared. Where omega in this case is the angular velocity, or angular speed, sorry, about the pivot point. Well, we have a moment of inertia here about some point that's not the center of mass. So let's do a little parallel axis theorem. So this would be 1/2 times the moment of inertia about the center of mass plus mh squared, where h is just the distance that we shifted from the center of mass to wherever the new axis is, omega squared. So h would be that distance right there. And for something that's rolling, that's also known as the radius. So that's equal to 1/2 I times the center of mass times omega squared, plus 1/2 mass h, well, we know that's the radius, r squared omega squared. And what's r squared times omega squared?
R over V, or something like that from that formula.
Yeah, it is something with that. What's the formula that you're thinking of?
I can't remember.
Set my alarm so that I don't suddenly realize class is over and I haven't handed stuff back or talked about Wednesday.
V squared over R? Oh, it's the centrifugal acceleration. Is that something?
No, we're not dealing with centrifugal acceleration here. Centrifugal acceleration is irrelevant to what we're doing here, I should say.
Okay. No, I don't know. Why is it irrelevant to what we're doing? Because we're finding this like pivot.
Well, we're actually, because we're looking at energy here and acceleration. If we were doing this from Newton's laws, then yeah, it might become relevant, but we're looking at it from an energy point of view.
Omega, is omega V over R?
It is.
Okay, so you can cancel out one, right?
So omega is V over R, or V is equal to omega R. So in essence, that's V squared. So what my formula for kinetic energy is 1/2 times the moment of inertia about the center of mass, omega squared, plus 1/2 mv squared. Because V is equal to R omega. If I think about any object that's rotating about an edge, the angular velocity of it, or angular speed about this point down here depends on how far you are away. When I'm saying that V is equal to omega R here, since this is the radius of the, let's just assume it's a sphere for right now. It could be other things, but assume it's a sphere. Since that is the radius of the sphere, we're talking about how fast it's going at the center. Which is just what we generally consider the speed of the object. So this is the speed of the center of mass. This is our formula for linear kinetic energy, which we just generally label as K. And this is the formula for the kinetic energy rotating about the center of mass, rotational kinetic energy about the center of mass. So when I solved the problem on class on Monday, a week ago, I sort of looked at it as separate objects, but that actually comes from ultimately the kinetic energy of an object rotating about an edge. And that's justification for what I did a week ago. or I should say, justification for my memory of what I did a week ago. Any questions? All right, shifting gears slightly, we're still dealing with the rotational stuff, shifting gears slightly. Now, the warning is that I do occasionally get bouts of vertigo. And now I'm going to spin myself. And so if I end up to the point where I will get dizzy, if I get to the point where it's not going away, I will excuse myself. I'll go into my office. There's a little exercise I can do that takes about a minute or so to help balance out the inner ear, and then I'll come back.
Is it that maneuver with the crystals or whatever?
It's basically, the reason I'm not doing it in here is that it just looks really awkward. I basically roll onto my head, and so my head is tilted basically downwards. All right, so I'm going to be rotating. I have obviously two books here. And if you've ever seen figure skating, you know what's going to come. So as I spin around like this and then I bring my arms in, what happens to them?
It's getting faster.
Faster.
All right, so why?
You're reducing the radius of the moment of inertia.
You're bringing mass closer to the center, so it's easier for you to go faster.
Okay, sort of trying to get to why. You mentioned one of the keywords. Your wording was off, but
Yeah, you're reducing the radius, and there's a inverse relationship between angular. I don't know. I'm probably mixing up all the terminology, but you reduce the radius, it's easier to spin.
oh, yeah. Let's see if we can combine it. By reducing the radius, what immediately? Let's not talk about the inverse relationship there about the spinning piece. Listen, if I go from here to here, what gets reduced?
The moment,
Therefore,
the moment of inertia.
yeah, ultimately. Because more mass is closer to the axis of rotation, I have a lower moment of inertia.
Is that somehow related to the door thing you did a while ago, where you like tried closing the door, and you were like, tell me how to close the door?
Oh, we could connect it. It's a little bit, it doesn't directly translate as well as I would like for this. If the analogy would be if I had a mass that was moving on it. So let's say I had a mass that was close to the axis, and as I closed it, that mass moved to the outside. That would be more closer to the analogy.
So does this have anything to do with torque, what you just did? Because when you say moment arm,
Yeah, probably not the better word. The distance from the axis to where the mass is. Yeah, you're right, moment arm. Ian should never have used that term, and I should never have accepted it.
it's okay.
So when we're talking about moment of inertia, the R is just, it's not radius, it's the distance to the center of mass.
Distance to the axis of rotation.
Axis of rotation. Okay.
So it is a radius in the sense that if that's my axis of rotation here, regardless of what the
Right,
shape looks like, it's sort of traveling around that spot.
Yeah, okay.
I stood up for a reason, and now I'm trying to remember why. It's gone. Maybe I just stood up. So as I am turning around and bringing the stuff in, I'm going around in this direction. Let's first look at it from a force point of view. From a force point of view, am I exerting more force on with my right hand or my left hand as I'm spinning around like this? As I bring the books in. Let's do it in slow motion.
More with your left,
Why?
because it's opposing the direction of rotation.
All right, let's think about the think about the movement of the books themselves. As I turn,
Oh, that one,
Never
the
mind,
one
it's
in your
not.
right arm has to travel further.
indeed. And that's part of the reason I'm sort of slinging myself in the direction in which I was going. And so as I bring my arms in like this, I am applying a force, or a torque in this particular case. I'm applying a torque in that direction, which does get me to speed up faster. We can go more sophisticated. It's a relatively closed system. Yes, there are other forces involved. There's some friction in the seat. If I started spinning it, it will stop eventually. But it's really actually pretty decent here. So it's going to go on for, a couple of rotations before it stops. So friction I'm going to consider to be of not particular importance. The gravitational forces here, but the gravitational forces are downwards. There are not any horizontal gravitational forces of any significance. And so I'm going to consider this close enough to a closed system. And in a closed system, what's conserved?
Energy.
Momentum?
Right. Closed system, momentum or energy is not necessarily conserved. But momentum is. But since we're dealing with rotational stuff, angular momentum. In a closed system. And we can demonstrate that slightly differently. So I'm going to get this thing to spin. What is the direction of the angular momentum?
Towards the door?
Yes. So when Ian, I first saw you do it. When I saw you do it, I thought your hand is backwards. You're using your left hand, but that was my issue. All right, so it's spinning around like this. My angular momentum is indeed towards the door. So if I turn it like this, what's going to happen to me? I'll lift my feet up.
You start spinning. You
So-
move some way. I don't know which way though.
All right, let's think it through. Let's make a prediction here. So if I have this thing spinning towards me, so spinning like this, and then I turn that way.
You're gonna turn to your left, I think.
Let's see. The direction of the angular momentum of the wheel now is
Oh, wait. Yeah. No. Yeah, it's down.
down. So I start out with my angular momentum in that direction. I turn the wheel, and so now the angular momentum of the wheel is downwards. What does my angular momentum need to be in order to,
Conserve momentum.
yes,
In the opposite direction?
yes. So if the wheel is spinning that way, so spinning like that, I will need to spin that way, which I think is what you had said.
To the left, yeah.
So let's find out if it actually works. It is physics, who knows? Probably just off camera, there we go.
Yeah, you are.
Oop, I think I turned it a different way. I think that's the way I did it. Yeah, because it's, see, that's going up, so I need to go in the other direction. Yeah. There we go. It works, physics works sometimes. Now, obviously, momentum was not conserved completely because we started out with angular momentum pointing in that direction. Which way would I need to spin really in order to maintain my angular momentum, or the angular momentum of the person, chair, wheel system?
Up or down, like,
Yeah, which way would it be?
Like this? You'd have to spin backwards essentially.
So the angular momentum was in that direction.
Yeah.
So when I moved it, I would need to spin in the,
Think
Yeah.
it this way?
I would need to
do a backflip with it?
go that way.
Wouldn't it need to be the opposite direction?
Because we start out with angular momentum in that direction, so I need to
Right.
maintain that. When I turn the wheel would no longer have any momentum in that direction, so I would need to
Okay.
account for it. Let's make sure I'm thinking through that right. So my angular momentum would need to be that way, so I would need to turn, feet up and back.
If you spin the wheel in the opposite direction so that the angular momentum is facing that way, would that affect which direction you go, or is it solely just the movement of like turning the wheel?
It's I sort of viewed your question two different ways, so try it again, or ask it again, please.
Does it matter if you spin the wheel clockwise or counterclockwise? Does that affect how you would spin to like match the angular momentum? Because we had it going this way.
Yeah, if I had going the other way, then it would just reverse
Okay, right. So you
the
would
rest
go
of it.
this way, even if you tilted it the same direction?
Well, let's be careful about that, the wording there. All right, so I had it spinning like this. So if I want the angular momentum in that direction, I have to spin it the other way. So as I turn the wheel, that is going to, so, stop. So spinning like this and turning the wheel that way, or spinning it with other direction and turning it that same way, I would turn oppositely to what I had done before.
Okay, right.
Does that answer your question?
Yeah, it does.
So the formula for angular momentum, what's it say? Linear momentum, what's the formula?
NB.
Speed. Sorry, mass times, yeah, that, way you go.
So angular momentum,
Divided by R.
Moment of inertia. Times,
Oh, right.
angular speed, omega.
is that
Yeah,
correct?
omega. It's, yeah. Angular momentum is equal to the moment of inertia